Good morning, everyone. I hope you can hear me loud and clear. Let me know so. Internet's been giving me a little bit of hiccups. I'm broadcasting live. I'm your host this morning called Christian Sasse. On behalf of iTelescope, welcome to this very special broadcast. And have a look at the comments. You can comment. In order to comment, you have to have a Google account and subscribe to YouTube, and then you can comment. So it's actually quite easy. It may be a little bit more difficult if you have a handheld device, but if you have a PC or Mac, it should be straightforward. Your comments are most welcome. First of all, I would like to thank Professor Myungshin Im. He's a director of the exploration of the origin of the universe. What a title. He's a professor of astronomy at the Department of Physics in Seoul National University. I, by the way, grew up in Seoul. Believe it or not, my father was a diplomat, so when I was a small child, I was in Seoul. But it was very different at that time. And together with Chang-Sung Choi, they provided some interesting data, which I'm going to go through this morning and show to you, because iTelescope participated in this major event. And I'm going to go through and hopefully make it exciting for you. We're going to look at original data from the telescopes. I'll explain to you how this was done and what is actually possible with iTelescope nowadays. So let's get going. So welcome everyone. I can see Marg is saying, good morning, good to see you, Christian. Well, good to see you all. By the way, yesterday we did receive a note from Larry Blanchard in New Orleans. He said he has been to LIGO Livingston, and there is an outreach to all the elementary and secondary teachers to participate in this major science event, which I think is fantastic. I mean, as you know, I'm completely in love with science, and this is something that we should propagate to the world. So what actually happened? I have this, what you see on the screen at the moment is very interesting, because this event happened in a galaxy called NGC 4993. It's seen in the constellation of Hydra, and what happened was two neutron stars. I'll tell you in a moment what neutron stars are, but they collapsed. And neutron stars are very dense, and as they spun around faster and faster, the frequency goes up, and that's what's shown there. That is an audio. That is the sound of the universe that they picked up at LIGO, and we'll go into that. And it's quite fascinating. I'm just going to play to you this last whoop. That's how it goes. Whoop. And my singing is not that good. I'm going to give you the original sound. What I've done is I put it on an audio track, and the audio track repeats itself. So you should use it as your ringtone. So just have a listen to this. Okay, so that's the repeated last sound. Again and again, this whoop. Quite amazing, isn't it? Quite amazing. And that sound is what this is all about. It's quite exciting. So let's get going. Now you've heard what it sounds like, and so I'll just have a quick look here. I've got several screens here. What you see here, the science community has been incredibly open to explain what has actually happened. So this is called the merger of two neutron stars, and they had this dance, and I'm going to show you an analogy to this dance, quite a beautiful analogy in a moment here on Earth. How you can imagine something like that has to be, but it's an analogy. A neutron star is very interesting, because what happens when a large star collapses, gets into its final life, a supernova is not the birth, it's the death of a big star. Protons and electrons, actually, because the gravitational forces are so dense, they are pulled together into neutrons, and it becomes what you call a neutron star. So protons and electrons combine to neutrons. And it's so dense, it's incredibly dense, that you have a teaspoon of this and weighs millions of tons. So typical neutron stars are the size of a big city like Chicago or so. But it's something we cannot imagine on Earth, nor can we replicate it. And in fact, it hasn't really been witnessed by science up to now, because what they actually caught which makes this event so interesting, is they first caught this bloop, the sound, and then they looked at the X-ray Fermi satellite, and they found that there was a gamma ray burst. A gamma ray burst is a very intense burst of light. And they caught that, and this the Fermi satellite looks at the whole sky, and they could correlate the two events. And what they immediately knew, which was quite interesting, is what happens here is these neutron stars are shaking space-time. Space-time is very stiff, and I will explain that to you in a moment. But what you see there is the ripples of space-time as these neutron stars were circling each other faster and faster, spinning around at higher and higher frequencies. It's unimaginable how this event actually looks like. But that's why there are so many beautiful schematics showing how this could have possibly happened. And then they merged, and then what happened after that is still under investigation because it is very complex. And there were a lot of events. When you read the scientific literature now, you'll find out that not all is clear what actually happened up there. But what did happen is, straight after the gamma burst, there was, so let me just show the picture. Straight after this gamma burst came out with very, very intense light, they started also putting the Hubble telescope towards this source of NGC 4993, and they asked all the scientists all over the world, and there were more than 3,000 scientists involved in this event, to take the telescopes and look at NGC 4993 and to see what is observable. And what is interesting, what is observable there is, and that is still ongoing, is it's interesting where all our elements come from. And I've got here a table called the Origin of the Solar System Elements. And you can see what there is in colors of brown and yellow. You can see there's merging of neutron stars. So whilst these neutron stars merge, a lot of the heavy elements like gold and so are formed. There's a lot of speculation that they say there's gold being formed up that's larger than the whole planet of Earth. Whether that is true or not, we can't check. But the data that they received, the optical data, and that's also very interesting, from all these telescopes that combined in the effort, more than 3,000 scientists working. The biggest effort that is known probably to science so far is the survey that they have, the Sloan survey. Yeah, that's what I was looking at. The Sloan digital survey, where hundreds of scientists collaborate, but they never had thousands of scientists collaborate like this. So this is a very unique event, and it's indeed very exciting. So, before we go to that, I want to show you quite an amazing experiment. Okay, we're going to do something like that on Earth. And I'm going to, what you see here is I'm putting the camera right down at the moment. And what you see here, and you can see, Christian, what are you getting at now? I have got something. Let me just put it up again. This is a heavy disk. This is a heavy disk. And this disk is on a mirror surface, okay? It's a slightly concave surface. And what I'm going to do here is show you an analogy. I'm going to show you an analogy of an event where you have a lot of potential energy, that's the massive neutron stars, being converted to kinetic energy, and then something else happens. So the potential energy is the weight of this heavy thing rotating on a disk. We're going to see a rotation, and then it's going to go sort of weird things. It's going to take quite some time, but the frequency is going to go up. And as it rotates faster and faster, it actually it actually dances on the surface here of the mirror. You will understand the analogy. It goes, similar to the neutron stars. I'm not saying it is the same. I'm just giving you some interesting, beautiful analogy of some mathematical toys we have. And I think this is absolutely my favorite. So let's get going. So I'm going to, let's see, I've got the light on at the moment. So I'm going to put this on a rotating disk. And oops, that's not how it's supposed to go. There we go. Now it's rotating. Just listen. Now, you won't believe it, but this event is going to go on for several minutes. So imagine this were some neutron stars rotating around each other. And as the disks gets lower and lower, the angle to the surface gets lower and lower, the frequency increases. And it's an absolutely phenomenally beautiful experiment. And what is amazing is that it actually goes on for such a long time. You've done the same with a coin when you rotated a coin, right? But the frequency is increasing. And soon, as the frequency increases, I'm going to hold a laser against it and I'm going to show you the pattern on the screen behind me. And you can hear how the frequency is increasing, okay? As it gets more and more to this so-called singularity. The singularity is where it finally touches completely down into the surface. By the way, this Euler's disk is named after the famous mathematician Leonhard Euler, an 18th century brilliant mathematician. And he also looked at these type of events. He didn't have such a beautiful Euler's disk, but believe it or not, this Euler's disk, and now it's getting a bit critical, so let me switch off the light now and try and see if I can show you this event now. Yeah, it's still quite large at the moment. So you can see some, I'm going to hold it at a low angle. Yeah, you can see something on the back screen, but it's still quite large. And I'm holding just a laser at one point, and here it goes. It's going faster and faster. It's still going. Isn't that amazing? So I'm trying to get the picture so that you can see it. And you can imagine this is something like two neutron stars rotating. So we're still going. And it's getting smaller, the circle, faster. Here we go. Whoop. There we go. Okay. So, I hope you enjoyed that analogy. I think it's just a beautiful experiment that shows something that we can do on Earth to help us understand what's going up there. Okay, so now let's go to LIGO itself. LIGO is the most miraculous and interesting large experimental facility that exists on Earth. Because, I mean, CERN has, of course, the particle colliders has been miraculous for many years, but now they've done something to detect gravitational waves, and it's been, there are numerous books written on that. And what is so interesting actually is you can see the extent, how long it has to be, and the reason is because light travels so incredibly fast, and in order to detect these type of events, you need a precision of, and now listen to this carefully, 10 to the minus 21 change. Now that's a 1 at the 0.0000001 with 21 zeros. It's quite incredible. So it's a precision that Einstein thought was impossible to reach. And how they did it was they built these very long arms, and they built an interferometer, which you see here. So what happens here is there's a laser source that is shooting out a laser beam in two different directions. There's a beam splitter, a typical Michelson-Morley experiment, only very huge and very sensitive. So they have this beam splitter and they split it in 90-degree directions. And what happens is, if everything's perfectly still, the beams cancel themselves out, okay? So there's no resulting movement whatsoever. And the light detector, which you see on the right, doesn't detect anything. However, if there is a gravitational movement of space-time, so space-time is being squeezed slightly to one direction, and it's usually shown very exaggerated, it's actually tiny squeezes that you can see, you will see a small mirror, and these mirrors, the mirror move, and these mirrors are suspended in a vacuum. It's an incredible experiment here. And they have to be so precise. And then the detector would see a small difference between one arm and the other because space-time is being squeezed a little bit. And I've actually spoken to a PhD student who works there in Louisiana, one of the LIGO facilities. And he's told me that during the upgrade, which they're doing right now to get it more sensitive, the dampening has to be even improved. Imagine just wind coming against this facility and causing vibrations. It's incredibly horrendous. Earthquakes, of course, and so on. But most of them are human-made noises from trucks and other things, from airplanes and so on. And they have to take care of all this. It's a horrendously difficult task. And these are just the results that they showed. This is a fact sheet. There's been so much put out by the scientific community. It's quite incredible. So you can see all the fact sheets. They call this the GW, the 17th of August, 2017. So that's the fact sheet that you find. Now, I'm going to, for just 1 second, we're going to take a look at Einstein's marvelous work in general relativity. As you know, he came up with the general relativity about 10 years or 12 years later after special relativity in 1905. He came up and basically postulated the Einstein field equation. And that's the Einstein field equation. Don't worry about it. But it does tell us something very interesting. It tells us how space-time curves on the left-hand side, called the so-called Ricci curvature tensor. And on the right-hand side, that is the mass and energy, like two neutron stars rotating around each other, and they are linked. So these masses are telling space-time how to curve. This equation looks very simple, but it is inherently complex. It actually consists of space-time, 3 dimensions, 3 dimensions for space, 1 dimension for time, so it's 4, and there are 2 indices. 4 by 4 gives 16 equations. 6 of these equations are identical, so in the end you have 10 tremendously difficult equations to solve. Really no fun, okay? And this has been occupying scientists for decades now because it's so difficult to solve. And we're not going to do this here, don't worry. But the argument really is, do you see this 8 pi g over c4? That is what couples mass and energy to space-time. And that number is very, very small. It's very small. And that's why I'm showing you this, because these sensors have to be so incredibly sensitive. So how small is that number? So if we plug in the numbers for that constant, 8 pi g over c4, g is the gravitational constant. Some of you may remember this from school, 6.67 times 10 to the minus 11. And c is the speed of light, 3 times 10 to the 8 meters per second. And you take a very small number, so 6.6 with 11 zeros before that, and divide it by a huge number. So small number divided by a huge number is a small number. And the number that you get is so small, it's 10 to the minus 43. So you have 43 zeros in that number. It's absolutely crazy. So that's how small this number is. So what this basically saying is, space-time is very stiff. It's not going to move. It's not going to move. It's incredibly rigid. But if you want to see it move, you have to build very sensitive sensors. And that's what I wanted to say. You may now say, well, Christian, I don't understand that because I've heard of general relativity before. We have them in the GPS. And indeed, if we wouldn't account for general relativity, that is the change of the gravitational constant as a function of height, our GPS systems would be completely wrong, and really wrong by meters, and after a while it would be kilometers and so on. The error would escalate very quickly. And then you've heard of the strange orbit of, not the strange orbit, but the orbit correction of Mercury and so on. And we've seen many other events. So why are these so evident? Well, this has not to do with the curvature of space-time. That has to do with effects of general relativity, which are much easier to detect and were already detected at Einstein's time. Okay, so these corrections are very important. But if you talk about the fabric of space-time itself and the curvature and how it actually moves. Then you look at this, at the constant there, and it at least on a very superficial level, that's all I'm trying to do, show you what's going on. Okay, fine. So let's jump now straight into sighting spring. Now that you've understood and you've solved general relativity, you know, whilst you have been drinking a cup of tea, we can now go to beautiful sighting spring. And I've been there many times. It's like my second home. I live here in Vancouver, but it really is the place that I absolutely adore. Why? Because the sky is so clear. You can see there's the famous sky mapper doing the digital sky survey. It's absolutely dark there, and you can see how beautiful that's looking, if I remember correctly, that's looking sort of more westwards. Yes, as the Milky Way slowly sinks in the early morning. You can see that, and you get this beautiful, you can see Sagittarius there with the sky mapper. That's another view of the sky mapper in the early evening. That's the evening. You can see our own galaxy there. That's our Milky Way. And then on the left, you can see the two satellite galaxies that surround us. So you can see how incredibly clear the sky is there. And what I was mentioning there is iTelescope, and that is what makes it so fascinating, interesting, was utilized in the days from 17th of August onwards to look at the events. And this was Professor Myungshin, who I mentioned before. And he's been communicating with us just a few days ago. This was a top secret event. And it also tells you how important it is at iTelescope to keep things running. And this is where I want to say thanks to Pete. Pete Paulus is the local lighthouse expert who looks after the telescopes day and night. And we certainly didn't know of this event, but we have to keep the telescopes up running all the time, especially for such events. So this was all top secret without our knowing. And what you're looking here is at one of the telescopes. And if you want to see what it looks like inside, the observatory is absolutely magnificent. What I did here is I put my camera there for one night, and I did an exposure, a combined exposure of the Milky Way marching across. You can see there from east to west. You can see that, and you can look at the center there. That's where the South Pole is. It's just shows you what a magnificent clear sky we have there. Now you may be wondering, what does this all have to do with NGC 4993? So the scientists, the science community across the world were told to look at NGC 4993. Now NGC 4993 is in the constellation of Hydra, and I took this image from iTelescope with a digital camera looking upwards, 30-second exposure, and that's the approximate position. I've just put a yellow circle there so you can see where it is. Now, the sky moves by 2 hours per month, approximately 2 hours per month. That means it's it's getting earlier and earlier, and all objects are moving more and more to the west. So the problem that the scientists had on the 17th of August was that NGC 4993 was very much in the west, about to disappear. They had about 1 hour window between twilight and darkness. This makes it so difficult. Why? First of all, it wasn't completely dark. Second of all, telescopes don't like to look into the horizon because the length through the atmosphere, the distortions you have due to refraction, light pollution, and so on become very difficult. They like to look up, especially large telescopes. But this is the advantage when you have smaller telescopes. You can do many more tricks. That is much more difficult to do with large telescopes. So that's also why small telescopes are utilized more and more, like iTelescope, because they are very sensitive, and they can produce amazing results. So if you have a look into the observatory, what you're looking at is the north wall there, straight ahead, the north wall. The roof has just gone back. To the right side is east, to the left side is west. So NGC 4993, the target, the host galaxy of this neutron star, would have been on the left side. And so if you want to look on the left side and you want to get past the wall, you need telescopes on the right side. Now, the lucky coincidence is that the telescope, there were several telescopes used. Mine was used too, by the way, so I was serendipitously involved in this amazing project. Of course, I take no credit for it, but I certainly take the joy for it. Okay, so if you look in the far left corner, let me see if I can just get an arrow here. Yes, I can. If I can point an arrow here, let's see if I can get this live. That is a telescope there. That is L50. Yeah, that's T52. That was used by this is the South Korean telescope, and that was used. So that was lucky because it's on the east side and they have to look west. Perfect, right? And by the way, a little bit further is T17. That's my telescope. Okay, and then there were some other telescopes. One of them used is the big telescope, the 70 centimeter telescope that we have. That's T27 and so on. A huge bucket. Okay, so they are standing in the center. They were all used, okay, during this event. And now I think you can appreciate how difficult it is because you're just looking above the wall into the horizon and you're just trying to get the last glimpse, and you need good weather. So lucky, everything was lucky in that because the weather was good, the telescopes were functioning thanks to Pete always running around and making sure they work, and everything just seemed to work, and it was top secret. And they were lucky that that some of the telescopes were not utilized. Of course, their own telescope wasn't utilized, but early in the evening, just after sunset, nobody was really operating the telescopes, or not nobody, but hardly anybody was, because most of the telescopes would be utilized properly when it is astronomical darkness. Okay, so let's jump in. Let's jump in now and see what the results actually looked like. So I'm going to switch computers now, and I'm just going to, so what you see there is I'm just going to put my own, because you won't see me now, because I'm just moving over to the other computer, but just let's have a look at the data. I'm going to process this with a software called CCD Stack. It's at the moment is my preferred software. For scientific purposes also you can use MaximDL. It's also absolutely excellent. But because I don't want to extend this forever, I'm going to quickly show you with CCD Stack how this is done. So what you're looking here is the data that was received from, and this is the original data, already calibrated. That means calibrated data means flats were done and darks were done. Flats is just to even out and calibrate all the pixels on the cameras, and darks are done to subtract the noise of the camera. Okay, so all that is done at iTelescope, and you can see, if you look here, I'm just highlighting the top one, you can see there are several ones called T52. I'm going to import them now, import a number of files and open them. So let's do it. So I'm importing them at the moment, and there you're already looking at one of the images. Now what you can do, and this is really important, is you can scroll through the images. I'm just going to open the so-called image manager so we can exclude some bad images. Okay, so let's just go through them. You can see these look fine, and by the way, on this picture is NGC 4993. It's right in the center. So I won't explain anything at the moment, but we're going to do a comparison. What are we actually looking for is the question. What are we looking for? So we're going to look at a galaxy, and we have to find something that looks different to the galaxy. If you've ever seen what a supernova looks like, you will see that there is a bright spot right next to the galaxy, and that's what we're looking for. So we have to compare our result, whatever our result's going to be, to a library result, and we have to see is there any difference. And that's what we're going to do now, okay? So what I'm going to do now is go through all the images, make sure they're fine. I'm going to select only the good images, and then we're going to process them. We're going to do what we call stacking. The stacking of images means we increase the signal to noise ratio, okay? So let's go through them one by one now. I'm going to the top one, and I'm going to, let's see, here we go. And we're just going to go through them, and you can see which ones are bright and which are not. This doesn't look very good, so I'm going to put a no. I don't want to include this image. And this is real science what I'm doing here, because This looks fine, this doesn't look fine, so exclude that. We don't want poor images, we only want the best image. Now images vary for all kinds of reasons. There may be atmospheric distortions and so on. You can see that image looks good, that image looks okay, it looks like there was a plane or a satellite that came through, but that's fine. This looks fine, this looks fine. That looks a little bit fade, but let's leave it. This looks weaker and weaker. This must have been in the early evening. Okay, so at the moment I've just excluded the two worst pictures here, okay? And the rest we're going to select. So I've done that. And now where is my cursor? Here's my cursor. Okay, here we go. Now we're going to stack the images. In order to stack images, they have to be aligned precisely. So that's what I'm going to do. I'm going to say register. Register means look at all the images and align them. So this is part of CCD stack, and it's got a very powerful stacking thing. It's done it, and it says, okay, I'm aligning them. The error is very small. And now I found some stars that I can align. And now let's apply an algorithm to align them perfectly. So I say apply to all, and this is going to take a few seconds, and there we go. And now they're all aligned. And what does aligning mean? So if I scroll through the images, which I'm doing now, let's see. Yeah, let's just do this. 1 second. There. They are now aligned. You can see that they're exactly on one is superimposed on the other perfectly. The stars are perfectly aligned. And now that we've aligned them, we can combine them. To combine them means it's like putting them all together. And these images, if I remember correctly, they were taken. These are, I think, 180 seconds images. Taken with different filters. What I'm doing here is I'm just combining all the filters. I'm not going to look at the details of the science. I just want to show you the result. And in the center, by the way, that in the center is NGC 4993, and we're going to have a close look at it. So let's do some quick stacking now. I'm going to say combine, and I'm going to take the sum, not the mean, the sum. I'm not interested in pretty pictures. I'm interested in results, so I don't want anything to get lost. So I'm going to say just produce the sum of all this. And there we go. And now we can suddenly see, and I'm going to expand this now, this picture, so we can take a closer look at NGC 4993, and I'm going to put it nicely in the center, and I'm going to just get rid of the other window here. And you can see this is the result that we get. 1 second. It doesn't seem to come across at the moment. Wait a second. It's not. Wait a second. It's not. 1 second. My transmission here is not working. I'm just going to say reconnect. 1 second. Ah, there we are. Now it's working. Okay, now it's working. From the one computer to the other, I just had it just got stuck, but now you can see the result. So you can see it's become a lot brighter and clearer. But what are we actually looking for? And now I'm going to do what we do in science is I'm going to look at the image, and that is NGC 4993 from a library. Okay, that's from the library. And now we have to compare them. But in order to compare them, I'm just going to blink backwards and forwards now. You can see that they're differently aligned. If you look closely, you can see that the galaxy has 4 or 5 very distinct in a row stars. So we have to look at patterns. And you can see there at the bottom here they're at the left. That means I have to first rotate this image, and then I have to get it next to the other image. And I'm going to do all this live now so that you can see that, how this is done. So I'm going to first rotate this so that it gets more or less aligned. Let's do it like that. That should be approximately correct. And now you want to also see it. So I have to bring this over a little bit to here. And then I have to crop it a bit. That's what I'm doing now. Cropping it so you can see it. And then I should enlarge the other picture quite a bit so we can put them next to each other. There we go. Let's do it a little bit more. And then let me enlarge the other picture. 1 second. bring up the scale a bit more. There we go. Now we can compare them. Now we can compare them. Okay. And you can see they look almost identical, right? You can see that. They look almost identical. So we're seeing nothing. You would say, well, I've seen nothing. Let's leave it. This is all, you know, this was unfortunately not successful. However, there's a lot more information in that image. If you look very closely at our object here, can you see at about 8 o'clock? About 8 o'clock, I'm going to put an arrow in now to help you look right here. Right here. Something is different. Something is different. There's definitely an object, okay? So even though we were under twilight conditions and so on, there is something that is different in this picture. And in order to see that, I'm going to invert the picture. Inversion, we much better see black and white. And then I'm going to sharpen the image. And there you go. Can you see it now? Suddenly, we have, you can see what details there are in the image. I'm going to put the arrow a bit closer, and you can clearly see there is a white dot, or in this case a black dot, right next to the galaxy that is not in the original image. And that's what they were looking like, right? So you can see on the left side, yes, on the left side, you can't see the edits. Okay, you should be able to, I hope you can see it nevertheless. I hope you can see it. Let me just close this here. Because I'm just reading your comments, you can't see the edits. I hope you can see the comparison now. You should be able to see it. So it's very clear that at 8 o'clock, stacking about 10 images, 8 to 10 images we stacked, you can see that it's about approximately magnitude 17 for those of you who are asking what magnitude is this. But you can actually see this on a single exposure too, believe it or not. If you analyze a single exposure, it already comes out. So you could see this in a 180-second exposure, but if you stack them, you can definitely beautifully see the result. So that's what I wanted to show you. This is absolutely amazing. So this is the merger of two neutron stars that gave the light, which was equivalent to the which was the same source where the gravitational waves came from. And that, I think, is really cool and exciting. What I'm saying here is the instrumentations that you have at iTelescopes are so incredibly sensitive that you can do real science with that. This was also, by the way, done with T30, with T31, and with T27. And I looked at T30. I'm not going to show you the results now, but we could also see the results not as good as with T52, because T52 is a very special camera, the same with T17 for scientific purposes. And it's not looking at beautiful pictures, it's looking at scientific details where the signal to noise ratio is better. But you don't get these beautiful pictures that you got of Andromeda or the Orion Nebula and so on. But you get scientific results. So I hope you enjoyed this excursion. That is, I'm just going to, let me just switch off the light here because I put on the light. So I hope you enjoyed this excursion and saw what is absolutely amazing. You know, that we got this original, these original data. Oh, I have to get rid of that horrible arrow. 1 second. You don't have to see where I am. But we got this original data from T52. And we analyzed it, and we actually get quite incredible results. And I think that's exciting. The scientific community is very different to the political community. It's very open, and it's there to share. Okay, and so I hope this has given you some inspiration of what is possible, and I hope you have at least got a glimpse of that and are excited as I was. So anyway, so thank you. Yes, Gentleman Ghost says Einstein would be proud. Yes, he would. Absolutely true. You know, if we could go back and tell Einstein that your field equations have been the most miraculous thing of the century, maybe of the millennium, whatever you want to call this. And look how far experimental science has come now. And experimental science and physics and astronomy is setting a lot of challenges to the theoreticians now. Because there are some strange things that they've detected. For example, they didn't expect the light curve the light curve that you see from the telescopes to last so long. They said after 24 hours it should go down. It did go down, but it went down much slower. There are some questions about why the gamma ray burst wasn't much more powerful, and so on and so on. Nobody quite knows what happened when these two neutron stars collided. Did it form a new big neutron star, or did it form a black hole? What exactly happened? That is still part of the investigation, and that is why these scientific observable data from both the audio and the visible and sorry, I should say the electromagnetic spectrum, which goes from X-ray all the way to infrared, all that data is so incredibly important. Okay, so anyway, I hope you enjoyed it. And if you have any comments, the whole event is amazing, isn't it? Yes, it is. It is. So thanks for joining. So I will go to the, let me see where my cursor is. Yes, here it is. So I'm going to say, have a wonderful weekend and thank you for joining. And whenever so do subscribe to this channel and do try some, if you haven't ever tried a telescope with iTelescope, try it. And if you need some private tutoring, I'm always there. Okay, so thank you for joining and all the best.